Hi everyone. So welcome to the CSP seminar this week. This week we have great pleasure to have Dr. Xiangxiang Xu who is now a postdoc at MIT, working with Professor Li Zhongzheng on representation learning. Xiangxiang received his bachelor and PhD from Tsinghua University, so we are alumni. And his interest is on information theory, communication, statistical learning, machine learning. And today he will be presenting some interesting work on deep representation interface for engineering problems. And I think he received a Best Paper Award at ITA early this year. So welcome, Xiangxiang.
Thank you. So today I will be talking about one question. It's about how we use deep learning to design engineering solutions. So let's see. Very good. Okay, yeah. So it's like elephant in the room. Everyone knows deep learning has been very successful in extracting useful information from data. And one specific thing we'd like to mention is that this data-driven approach puts very mild assumption. So we don't need to know how data is generated. Instead, we just learn everything from data and works quite well in practice, particularly in vision language tasks. On the other side, we have many engineering problems that share some nature. Like if we look at communication, the model is getting more and more complicated from the original Gaussian model. We are going to non-Gaussian model if you change the frequency. And now we have more complicated data, like the fading coefficients of the channel could have very complicated statistical behavior. So in that case, typically requires nonlinear decision if we have multiple users. So that's some common nature. And there's one natural idea to use deep learning approach in solving this engineering problem. However, we would soon find that there are some challenges very special in our engineering designs. Say for communication problem, we have like very strict performance requirements. And if we think about the communication, the bit error rate or the kind of error we can tolerate is much, much lower than typical calculation problem. So that says we are concentrating on some real event. So if we use end-to-end training, the loss function might not even be sensitive to your network. And we need to adapt to different scenarios. Say we want to do communication. The channel is changing over time when you move around and when the environment change. So in order to have communication successful, you need to deal with not only one channel situation, you deal with all different channel situation. So it's much like the multitask learning, or you think of you want to train one model for different tasks. But somehow we also have constraints in the sense that we can use only very limited resources. For example, if we think about multitask learning or just adaptation, a common practice in machine learning is you just take 10 new samples to adapt to something new or just fine-tune your model a little bit. But this kind of practice could be very difficult in communication because the so-called samples in communication is actually a cost or the overhead in communication, which means if you have many training samples, you already know what you want to communicate. So that is not informative. So somehow that's against the current practice we use deep neural nets. Since deep neural nets most work end-to-end way, and that's solving specific tasks. But now if we want to turn this to an engineering solution, we would like to have more modularized design, mostly for stable performance and also for better control of the performance. So if we think of the simplest design like modulator or filter in communication system, it's all general purpose in the sense that there would be no filter specific for one communication system. It's specified by a few parameters, but compared with what we get in deep neural nets, each layer, if we pick one layer out of the trained network, it can only be used in this network. You can hardly imagine you can use this layer for another network or for another task. So this gives you a tension. And On the left side, we can see that deep neural nets, for this reason, often be called as black box. For the right side, the reason we get nice analytical model, or the reason we get the nice separation or the modularized design is because we have very good analytical model, in the sense that we can have more structures in this design. So let me just give you several examples. So imagine we have a bandwidth limit signal and we do sampling. And we know if the sampling rate is high enough, we can reconstruct the original signal. So in this sense, it's not the high dimensionality gives the challenge. Once we can identify the structure in the signal, then we realize more samples do not give us more information. And it just causes a shift in the frequency domain. So instead of deal with the signal in the time domain, we can look at this in spectrum in frequency domain and get a spectrum. And that gives us one way to deal with signal in a more unified way, and we find more convenient. In that sense, we are using the frequency domain or the spectrum as the interface for dealing with signal. And another story comes from data compression. Suppose we have an ID sequence of nx samples, and the way we turn data or compress data into bits is we just concentrate on so-called typical sequence. So in short, if you have a long block of sequence, most sequence would be typical. And by looking at this typical sequence, we will find that they are of almost equal probability. And the more interesting thing is the essential result is given by law of large numbers. So in communication setting, mathematically we would prefer longer and longer blocks. So it's not the reason the long block is not the reason we cannot deal with good. For both examples, we can identify that what we really hope for the interface is to identify the structure of the thing we want to deal with. So if we call that as interface layer, what we require for the interface, first thing, we want to keep all relevant information. And if there be anything irrelevant or redundant, we want to remove them. That's like the case we did in data compression. And second thing, not only we want to keep all relevant information, we also want to have very convenient and efficient processing, in the sense that you can have 10 similar representations of the same information, but you don't want to use another 10 steps to process that interface. And also, the interface should be multiple purpose, not like we are just using the interface for one task. Otherwise, we cannot reuse that for different designs. And fourth thing is this has to be robust, in the sense that if that's mathematically defined, but very sensitive to any estimation error, then it would be useless in engineering design. So if we check the principles in both storage, sampling, and data compression, we find that both spectrum and typical sequence gives you a way to reconstruct the original information. So in the sense that they keep the relevant information and can be served as multi-purpose design. And in processing, we find that by looking at the spectrum or frequency space, we convert convolution operation into the multiplication, which means any kind of filtering operation or linear time invariant system can be converted to some multiplication on spectrum. That makes the processing very convenient and efficient. And in data compression case, since we already encode data into IID balance bits, that's like no binary sequence is different from the other binary sequence. So we can process them in a fairly symmetric way. And in robustness, we can find that the sampling, we are convert the time domain to frequency domain, and we know this is a orthogonal transformation. So everything we lose in the frequency domain would just be equal as we lose in the time domain, which means we can allow the error in the frequency components, and the error is the same and will be reflected in the time sequence. And in compression case, we could have robust design by introduce error correction. So in this talk, I will try to introduce a modular learning design that is a design based on deep neural nets for solving engineering problems. And the basic idea is trying to build an interface on feature representations. So in the first part of the talk, I will talk about the mathematical structure and how we learn such an interface from deep neural nets. And second part, I will talk about the mathematical framework to extending the framework to deal with multivariate dependence. And at the end of talk, I will present a case study on a very classical problem that's multi-user detection in wireless fading channel. And I will talk about the deep neural net-based receiver design. So to start, one thing we need to realize is once we need to use neural nets, we better understand what neural network is doing, though itself is a tough job. For example, when we do classification, we want to know this image as the image of espresso instead of pizza or other stuff. We can apply a convolutional neural net like here. So we need to have a certain mathematical simplification to help us understand what this neural network is doing in order to get better solution in a more principled way. So following the doctrine of Shannon put this in his 1948 paper, saying that it's first necessary to represent all those messy elements into abstract or simplified mathematical entities. So they serve a purpose in conceptually understand the complicated phenomenon. So if we look at the picture, we can see many parameters, many layers in the middle, but eventually at the end of the day, we end here. And here we can abstract this as a transformation from image to this layer, which we call the feature. So by applying all these layers, eventually we want to get some good representations from the data, and that's a feature. So we can abstract the learning process as learning features from data. So in this case, data is a pair of image and label. After learning some features, the prediction or the learned model becomes an assembling on the feature. So for example, in this case, the classification task is actually conducted on this layer by using also the weights in the layer. And a more symmetric view, you can also view the weight as a feature of the label, since by projecting the feature to different directions, making us able to identify those different probabilities. So in the sense that this all weights connect to the espresso gives you a feature of espresso. With this view, we can come back and ask in this setting, if we abstract everything, so X would be our input, Y would be our target. And we want to learn some feature to predict or infer about Y. So this Y hat could be something in estimation or could be something as classification. So you could have estimate different target or different functions of Y. So we would like to ask this question, what kind of fx if we want to use it as an interface for this task? So first thing, as we mentioned, f should contain all relevant information and doesn't have irrelevant information. And that translates well to the concept of minimum sufficient statistics. If fx is the minimum sufficient statistic of x in inferring y, then everything about xy dependence is containing fx. So that could be a good candidate. But we know that minimum sufficient statistics are not unique. So next thing, if we check how we process the feature, we'd like to have more efficient processing. So the simplest processing we could have is we suppose this prediction module is just a linear module. So we would like to have some f such that you only need to have some linear combination on f, or in other words, if you want to train neural nets, you would like to train a single linear layer on top of f for your inference. And now the third thing is we want the thing to be robust. Say fx typically is a high dimensional or vector valued feature in the sense that it could have like 1024 dimensions. So in that case, the thing we would like to do is even we discard, say, 200 dimensions over like 1000 dimensions, we hope to not lose much because somehow we believe if the feature has a structure, we can safely ignore the unimportant part. So it turns out there is indeed only one feature would satisfy all this criterion, basically the first two criterion. If we restrict to minimum sufficient statistics and also want to have linear inference, turns out it gives a conventional concept of HGR maximum correlation. So here's how we can construct this interface. We start from looking at all one-dimensional or scalar values features f of x and g of y. And we would pick the one that's maximizing their Pearson correlation coefficient. Since we know Pearson correlation coefficient is restricted to only representing the linear dependence, but by optimizing over f and g, we would get the best f1 star and g1 star that maximize the correlation. And we would like to normalize them to have zero mean and unit variance. So the sigma 1 would be expectation of their product. So this HGR maximum correlation has a nice geometric interpretation. If we think about X feature as a linear subspace and Y feature as R one-dimensional function of Y is also a linear subspace, we can compute the principal vector and the principal angle of these two spaces. And that will give you F1 star and G1 star. And you will realize the cosine of this angle gives you sigma 1. So it's always between 0 and 1. So here we use the product as a definition of the inner product. So recall that these are all functions of x and all functions of y. So we can identify their intersection as constant feature. That's why we want to restrict this f and g to be zero mean. So they won't be getting the cosine 0, which is the first mode, trivial mode. As they are high-dimensional space, we can continue this process. If we want to find the second pair, which we call F2 star and G2 star, we need to restrict them to be orthogonal or uncorrelated to the one we just got. So we will get some F2 star here, some G2 star here, which I cannot visualize in the two-dimensional screen. But in high-dimensional space, you can find the second pair and the third pair up to you get all these pairs. So that gives you the set of maximally correlated features. And one final step is we want to stack everything. So each of Fi star is one-dimensional output. If we stack them, say they have k-dimensional features, then this F star and G star would be the k-dimensional output. We can prove that this F star, G star actually give you minimum sufficient statistics. So that's a minimum description of XY dependence, in the sense that if you want to capture every information, then you need to be at least as good as F star X and G star Y. And from an algebraic point of view, because we are computing the principal angles and principal vectors of the two space, so the algebraic meaning is to computing the singular value decomposition of their gram matrix. So their gram matrix would give you something like the density ratio. So actually, what we have computed would give you the singular value decomposition of this density ratio, in the sense that Fi star X and Gi star Y would be the singular vectors, but they are infinite dimension vector in the sense that X can be continuous, Y can be continuous, and sigma I would be singular value. And now we can see why using the F star and G star, we could always have linear inference, because we get a bilinear form of the density ratio. And we can also show that if we want to truncate the feature, saying that we just keep top k of the F star and G star, we would get also optimal representation in the sense that they are the best k-dimensional features. So from the SVD structure, we can show that the posterior or likelihood will just be the linear form with respect to either F or G, in the sense that if we want to do prediction, ranking, or estimation, everything would happen in this feature space as bilinear. And if we want to do any estimation, say you want to use X to estimate some function eta of Y, could it be cosine, sine, or exponential? But since this conditional expectation only has to do with py given x, which is bilinear with respect to f and g. So this gives you a linear combination of all fi star. In that sense, fi star is actually orthonormal basis of the space. So geometrically, this has a nice interpretation in the sense that if you recall the y features gives you a subspace, and the conditional expectation corresponding to projecting this eta y to X space, since this is the MMSE solution. And we know that all these principal angles have given you a basis of everything that's related. So that's why this Fi star are giving you the orthonormal basis. And from the SVD structure, we can easily see that those singular values are ordered, and that actually gives you the different modes and their strengths in a monotonic way, and different dimensions of f and g. Yeah.
Yeah. So x and y are two like instances of like feature vectors, right?
Little x, little y for this one. Right. Yes.
Yeah. And can you perhaps comment on the relationship of this to copulas, which contain the like the joint information?
Yeah, good point. So basically what copula did is if x, y are like one-dimensional, I believe, then you can write their joint CDF as the functions of their marginal CDF. That gives you copula. But one difference is if your x and y are living in high-dimensional space, then the copula, the definition of copula is not well defined, or either you have to treat them as a set of variables. So it's basically sensitive to the coordinate system. But if you compute the xy actually density ratio here, then you will realize the changing of coordinate system won't change the behavior of this decomposition. So that's one property I didn't mention here. If we think about computing the principal angle, if you have some transformation on x, say you map x to exponential of x, then the feature space won't change. It's just every point have a different name. They have a different coordinate. So this decomposition is invariant to transformation, which I think is more fundamental in some sense. But it also has some other computational advantage I will mention later.
Thank you.
Yeah, for special case, if they are all like on real line, then they are kind of related in a nice way because you can compute the copula density and you get the same thing. So from the SVD structure, we know that different dimensions are uncorrelated, just in the sense that the different singular vectors are uncorrelated. And even we take one dimension from F and one dimension from G, if I is not equal to J, they are also uncorrelated. So that gives you a nice covariance structure. And in terms of the robustness, here is a connection. That is why we can claim if we do a truncated version, we just cut to like top K. And we can claim that the top K F star and top K G star will still be optimal K dimensions you will get in the sense that they give you the rank K approximation of XY. So that's basically the relation between SVD and low rank approximation. So in the matrix case, that happens if you want to compute rank K approximation of a matrix, instead of having a function, having a package compute for that, what we would really do is first compute SVD, and we have a truncated SVD, and we know that's the best rank K approximation. So for this case, the best rank 1 approximation would be this, best rank 2 would be just taking the sum of first 2, and rank 3 is as a sum of first 3. So up to this point, we have verified the F star and G star constructed in this way has satisfied our desired properties of the interface. And for this specific property here, it's very useful in like vector database. So say X and Y are both real data like images and or sentences, then we would like to store their embedding in vector database. And if we want to do some retrieval tasks the computational storage cost would be proportional to the length of dimensions. And on the other hand, we know that longer dimension gives you better performance. So in this sense, this ordered or structured feature actually gives you one way to achieve the optimal performance cost trade-off.
Does this also give you like different hierarchical like levels of relationship? Like if two things are rank 1 associated or rank 2 associated, maybe the rank 2 is like a better, I guess, think of it like farther down on like drilling down further into similarity, or is that not?
It's not directly related, but by putting additional assumptions, you could have that structure, because hierarchical is it's like stronger assumption on the data structure. It's like, say, if you just put join Gaussian X and Y, then that kind of hierarchical structure might not happen.
Okay, thank you.
So up to this point, we are all talking about the mathematical construction of this interface. And one thing we need to ask is how to learn such features from data, since your X and Y are not something you can easily tackle. And mostly we don't know the density ratio. So in the next few slides, I will talk about how we use neural network training to learn the HGR features. So first thing to keep in our mind is, though we talk about this maximum correlation by maximizing Pearson's correlation coefficient, it's not efficient to directly use the Pearson correlation coefficient as your loss function. So actually, this work has been done in earlier, and it's called DCCA. As you may have heard of the name, if we do the same maximum correlation, but restricting all the features to linear features, then that actually gives you canonical correlation analysis. So the earliest extension using deep neural nets to compute the HGR function is known as deep canonical correlation analysis. So directly using that would give you bias gradient. And if you want to extend to latter modes, that's more problematic in the sense that you have to keep maintaining the wide structure. So you need to whitening, which means you need to compute the inverse of covariance matrix. And that's not very scalable if you have like 1,000 dimension of features. So instead, an easier unconstrained formulation is, if we forget about the structure, we just care about the rank K approximation, which is we just want to find K-dimensional features F and G such that their dot product gives you the best top K modes. And that can be formulated as an unconstrained formulation, because here F and G are free. And the only thing we need to note is in this way, generally different singular modes are mixed, in the sense that you cannot hope the first dimension of F would be the best F1 star here. So you will get a mixture of all K modes, except for setting K to be 1. Mathematically, that's very similar to the matrix factorization or matrix completion problem. But here we need to know that we are factorizing something we actually don't know much about it. RxY is a density ratio. And in practice, we only have samples instead of like this nice matrix. And samples are typically very sparse in the sense that you cannot hope any X sample to appear twice in your data set. That's one challenge. And your output, instead of this maybe 10-dimensional features or 10-dimensional vectors, you now have infinite long dimensions. That's why we need to use neural nets to represent the feature. And computation-wise, we can still do the distance minimization formulation if we define this norm to be a distance in the function space. So here, I is a joint function of X and Y, and we take the outer product defined as this. So we can get a sum of K rank 1 modes here, and we need to minimize their distance. And the optimal solution, as we know, will give us rank K approximation of I. So the good thing of this objective is we can easily convert this objective to a valid trainable loss. if we compare the difference of the approximation error with I squared, then the I squared, the norm of I itself get canceled out. And we only get cross term and the square of the F out product with G term. So if we have n samples xy, then we'll find that this H-score objective corresponds to just covariance of fxgy and some variance of f and g. So this gives you a trainable loss function. And in implementation, the only thing we need to do is to compute the empirical average of both terms on a batch of n samples. So that can be done in 10 lines of code.
Can you remind me, how do you get rid of I?
Because I is density ratio.
It's what you don't know.
What you don't know. But now the norm or the inner product is defined with respect to their product. So after the expansion, the denominator and nominator get canceled out. You only have pxy. So you are doing a sum over pxy, which is the expectation of x fx times gy. And the way to estimate the expectation is done by the empirical average.
I thought that f and g were scalar, but were vector valued earlier, but they must be scalar.
Yeah, in one-dimensional case. So for the ease of presentation, this line is for one-dimensional case. But in the code base, you can see this is for vector base. So you have to deal with covariance, and this has to compute f times f transpose.
And then you take the trace of the covariance.
Yeah, the trace of covariance. Yeah. So degenerate case is like just their product. Yeah. Nice question. So that gives you a way to learn the top K modes from I, and even you don't know why. So let's see, the network texture would look like this. We have X and network F to generate some feature from X and Y and GY here. And we use H-score as our objective. That would give us a low rank approximation or factorization of I in this form. For example, if we just check it on MNIST, then X would be the image, Y would be the label. And we can use two-layer convolutional neural nets as your F. And here G, suppose Y is one hot encoded, then you realize you only need one linear layer to express all possible function of Y. So if we compare the structure, it's like we flip the last layer of traditional classification network like cross entropy loss to the right side and have a symmetric formulation. So here's what we can learn from the H-score. And for comparison, we can use the same network and compare it with the cross entropy ones. And here's a visualization for the learned representations. And it's 10-dimensional, but using Chisney to reduce to 2-dimensional for visualization. And we can see that H-score training can better push different classes far apart. And mathematically, that's because we are doing maximum correlation. And the maximum correlation is equivalent to maximizing the between class distance and minimizing the within class distance, if we assume both features have normalized length.
So your training only uses this H-score. You're not training a classifier per se, you're just training the embeddings?
Right.
Okay.
But it's labeled data, right? You know the
label.
So it's supervised in that sense, right?
Oh,
Right.
it's supervised?
If you define supervised to be anything with label, then that's supervised. So here you have Y. But if you want to have another image here and want to learn their dependence, you can replace Y by another image. Just replace also this G by some network. Yeah. So in this formulation, X and Y are totally symmetric. That's one advantage. So if we have two images, we can do the same thing, and that can be.
Visualizing the feature, are you visualizing the feature for F or for G?
This is the F.
Oh, F, okay.
Yeah, because you have different digits. I mean, for G, you only have 10 choices, so there would be 10 points, because Y only have 10 choices. So I just put the real image on top of the feature, so to see how they are grouped.
So in this way, you learn the feature, it doesn't collapse?
Doesn't. Yeah, I didn't overtrain in that sense. Yeah, if you overtrain, it will collapse. That we can prove.
What do you mean by overtrain?
Overtrain meaning you are repeatedly saying the same sample, and it's like you train the classifier to be really good at identify them, and then you will realize the maximum correlation solution or the minimum sufficient statistics will just be the point or the right label.
Oh, so you need some early stopping to minimize H-score.
It's not like that. It's like if we just apply the same iterations to train cross entropy, we use the same optimizer, same setting, and get the result for the fair comparison. If you overtrain for both cross entropy and H-score, you will get collapse result. That's what we call neural collapse. So let's get back to this new question. If we have this cross-domain retrieval task, which you want to retrieve the image correspond to the sketch. So in this case, both X and Y are continuous, but we can apply the same network architecture just to use both convolutional neural nets to express your FNG. And we can find that H-score can give you better performance than previous designs. Even previous ones used generative model or additional information. So the last step we need to get is how we get back to SVD by only having low rank approximation solution. Because now we know if we use k-dimensional FNG, we will learn rank k approximation. But the SVD has an additional layer of this ordered, structured, and orthogonal feature dimensions. So the easiest thing to do is if we just have one-dimensional F1 and G1, we train H-score. And now we know the rank 1 approximation gives you a first mode. So it doesn't make much difference in the sense that you will get F1 G1 as a scaled version of this. But up to the second mode, we know that if we train two-dimensional F and G, we will get some of this. So in order to get rid of that, we construct a nested structure like this. So the second dimension would be fed to the network in this way, in the sense that we have the second H-score, but the input is a concatenated F1, F2, the two-dimensional feature. And here is two-dimensional G1 and G2. So if we just look at the second H-score, we will realize the optimal solution is when you have the sum of two modes, F1, G1 plus F2, G2, is equal to the optimal one, which is sum of S1 and S2. So if we have these two conditions satisfied together, then the only solution would be the first pair gets the first singular mode and the second pair gets second singular mode. And the good news is you don't need to wait for the first score to converge to train the second score, because even you maximize the sum of two H-score, the only common solution would be the solution, would be our desired solution. So you can have a joint training that learns the order structure. By extending this,
I was just gonna ask, you need to know like which one corresponds to like the first rank, which one corresponds to the second
right?
rank.
That's
How do you force that order?
You don't need to force, it's just the index system, right? If you have a network output 100 dimensions, you just name this as 1. And if you don't like this, you can have another indexing system. But they have to be consistent.
But like, how do you ensure that the second output is not actually what should be the first rank?
It's like in computing this, you can see your loss is not symmetric to first and second. So if we call this as first one, then this would learn the first mode.
Oh, so it's a rank 2 up to some permutation. You don't know exactly which one.
No permutation. Because say you have only two-dimensional output.
Right.
And that's the first one. You have one H-score on the top.
Right.
But for the second H-score, you are accepting both in the sense that the F2 is not connected to the first one.
Okay.
So they are not symmetric.
I see. Thank you.
Then you can extend this to high order modes and get the k-dimensional output as ordered. And the optimization is the same. You just maximize the sum of the H-scores. So this gives us a case where we can use end-to-end deep neural network training to get some structures. Compare with the traditional way, like if we do Gram-Schmidt or we do postdoc processing, we need to first get something and have another layer of processing, yet we don't have guarantee of what we would get. So this gives us one suggestion that by controlling the loss, we can actually control the information structure happening here. Yeah.
So in principle, F1 to Fk should be like K different networks, or
that's your design choice. If you just use one convolutional neural net and use K different outputs, that's also fine. But you can also have disjoint designs.
But the theory should be like optimal overall, like.
Right.
So if you are sharing the weights.
If you are sharing, that gives you a trade-off between the training efficiency and kind of, generalization. So if you don't share anything, you will learn some delta function. But having disjoint network is also a design choice. So here's what we can do by doing the same example, but learn order results. So we can see that the retrieval precision would be a function of your feature dimension. And if we do the nesting, we concentrate the information in the first few dimensions. And we can find that by using only 1/4 of the actual dimension, we can get almost the same result. And at the virtual setting, if you use 1/4 on the bottom, then you get almost nothing, as if you are learning a random guess. And the middle line is if you do unstructured learning, then you get something significantly worse than the best 1/4. So next, I will quickly talk about how we extend this framework to multiple variables. As we have mentioned, in communication, we also have side information like the fading channel coefficients. So first, one thing we can consider is we just talk about how we factorize this density ratio or joint function. Actually, a more concise view is the factorization is a specific case of operation on the joint function space. To formalize this idea, we can define the geometry on the joint function space, which we call feature geometry. If we define one inner product as the expectation of two joint functions on their product distribution. So we can see that the induced norms and projection will be well defined. And if we just consider the norm or projection or geometric structure on X feature or Y features, that will boil down to the previous structure. So now it gives us a different view to read what we did in computing the low rank approximation. Say we just optimize the G function for a fixed F, and we get the result as some single-sided H-score. Then we can show that the single-sided H-score actually gives you the projection of X, Y to the space. It's a space defined by the bilinear product of F and any function of G. So in that sense, this gives you a metric captures how much information F carries. So the information is in a specific sense that this information can be used through some linear inference. So this gives a way to quantify the information content when we take the processing into account. And we can further extend this. One good thing about feature geometry is now we have a unified view to deal with statistical dependence as joint functions and the feature learning as learning some functions of X and Y. And joint function corresponds to the tensor product space of the feature space. So we can further define function space operations on the dependence, saying like projection. If we compare the feature geometry with our conventional view of signal space, that's like a space of all waveforms, we can find that they share very similar geometric concepts. We can, the inner product and projection can be defined for both space. However, the feature geometry can allow complicated topology of alphabets in real data. Since in real life, it's hard to identify what alphabet X and Y can be, but in signal space, the alphabets are always, or the collection of inputs are always like time domain or one-dimensional real line. And now the inner product is defined to reflect the data distributions in the sense that for data-driven approach, it can better reflect the relations between different features. Compared with signal space, we just treat everything uniformly. So now we can get a slightly different setting by extending the framework to deal with the third variable, which we call side information. So if we want to do the same interface or inference task, but we require the inference part can also access some side information S. So this can correspond to different tasks like the symbol detection. And you can see that I now put Y as the input, X as the output, because that's like solving an inverse problem. And this is directly related to the communication or decoding setting. And in learning setting, it's related to the distributed system. If your agent can collect some information, extract a feature, but the server has some additional side information. And if S corresponds to the task ID, this can be also related to multitask learning, because you want to do the same task, but supposedly conditional on different tasks, you have different distribution. And the task we want to do is to learn a shared representation. So from an information point of view, what we really want to do is have some decomposition like this. We have the information between Y and SX, but we want to identify which information is only related to what S, and we want to subtract that part to get the conditional part for our inference task. However, we will realize the scalar relation doesn't tell us much about how we should learn features. So instead, with the feature geometry, we can convert this to a similar decomposition in the dependent space. So we can think of this YSX dependence as a new joint function of YSX defined as density ratio between the two parties. And turns out this YS then would be a specific instance also in the space, that's YS dependence. And we can show that mathematically this IYS corresponds to the projection of IYSX on this Markov plane, in the sense that each point of this plane corresponding to a distribution that's satisfying Markov relation. And the vertical part, which is your approximation error, reflects the conditional dependence. So we can show that the conditional dependence, this vector vanish if and only if you have this Markov chain. And by taking their norm, the Pythagorean will tell something similar to the chain rule of mutual information. To learn the conditional information and the joint one, we can use the similar nest structure. And recall that this is actually want to do a subtraction in the high dimensional function space. We want to really do subtraction between a tensor and a matrix, and they are all infinite long and wide. So we can apply the same nesting idea, first learning YS dependence by H score, and then we do nesting and learn YSX together. So here, F can accept S and X as both as input. And this nesting would give you optimal solution such that this G bar and F bar would only learn the YS dependence, and this G and F will learn the conditional one. And learning can be done similarly, and by assembling different modules, we can get estimation of the conditional dependence and also get all the posteriors. That would be our basis to design a network-based, neural network-based receiver for communication task, as I show here. It's called multi-user detection. We have two users, X1 and X2. X1 would be the desired user, X2 would be the interference. So suppose X1 take BPSK, that's 2 values, and X2 take the 16 values, 16 QM. Their sum would be something like this. So that's like 32 clouds. And we want to identify whether a received point is red one or the blue one. Here are a few examples. If we think about the problem, the best thing we can do is map prediction that's based on the posterior. And if we can do map, suppose we get a signal like this, the boundary will be like this. And we can see linear also performs good. That's optimal linear decision. But if you are unlucky, you get some case like this called deep fade. That is when your interference is too large. So you can see if we apply map, you will get some highly nonlinear boundary, but you are still identifying the different symbols very well. And if we change it to a different fading, you will get a different boundary. So I think I should wrap up quickly. Right? Okay.
Sorry.
Okay. For the sake of time, we will just go through the results. So with the nesting structure, we can deal with dependence and conditional dependence between your received signal and your sent signal conditional on the channel coefficients. So if we think about this as learning test, the real difficulty is not to distinguish or write this nonlinear boundary for one single neural net. The real difficulty is you want a solution that can adapt to all different channel solutions. In the sense that because your online symbols are so expensive, you would like have one network that can solve all these different boundaries. So here's what we can get by training this receiver. I will talk about training details later if you are interested. So we can see that if they are well separate, then we can learn the boundary well. And all the thing outside has very low probability, so it's learned like worse. And even we are in the deep fading case, we can see that those boundaries are still well separate in the sense that we can identify the points. And let's change a third situation. We can see that the receiver can adapt to different channels, though the channels are randomly generated and unseen during the training. So if we want to have a quantified result, we can plot the BR under different channel gains. And here we fix the radius of the channel gain, and we can see that the performance is actually not monotonic in the sense that this constellation are interleaving with each other. So you will see this up and down, up and down. And when interference is actually strong, you can get actually lower error. So this intermediate one would be harder. And let's consider two extreme case for very low interference, it's close to linear decision, so everything performs similar. But if you have very high interference, the deep network receiver can still perform as good as optimal one, but linear ones would suffer. So here are some training details, which is important because this is not a problem we are given the training data. In order to highlight the deep fading events, we should set the distribution such that the network has seen enough good hard case in their training. Otherwise, if you just care about the average result, you will find they perform almost equally good. But in communication, we mostly care those hard cases. That's like the bottleneck of the performance. And in network architecture design, we can use Fourier feature to generate some more nonlinear boundary in the sense that if you just use MLP, it doesn't perform as good. And since we know the system model, we can plug in our knowledge to generate some feature for the model. Say this F should not be arbitrary F like MLP, as we know that this H1x1 plus H2x2 is a sufficient statistics. So we should have similar form or transformation form to plug in here. That's how we incorporate our domain knowledge. And this example shows that if we just use average case like really fading, then you get smooth result, not like this more like fine-grained characterization. So a special case is out of distribution, though during training, we never see the zero interference case, but we can still test and we can see that the receiver still performs well up to some point, and the BR is relatively low up to this point. And if we want to further improve the performance, we could add this case in our training data. So that gives a way to inspect different cases and to have this knowledge to feedback to our receiver design. And in summary, we need to separate the feature learning and feature usage to have more flexible and controllable modular design. And to get good performance, our training setting should not be exactly the same as practical scenario, because that would average out the performance and not get some interesting results. And by understanding the feature learning process, we got a way to incorporate our system model or domain knowledge into a network design. So we are not just forcing the network to blindly learn some functions. So there are some extensions if you are interested we can also extend the setting to sequential dependence and multimodal dependence. And the SVD problem can be extended to solve general SVD or partial differential equation. So we have tried this on Schrödinger's equation and have a paper on SML if you're interested to check. And the understanding itself can be useful in understanding what representation we learned in pure learning tasks like supervised learning, self-supervised learning, and unsupervised learning. And this also helps provide an interface for more principled adaptation of representations. So I will conclude my talk here, and thank you everyone for coming.
Thanks, Xiangxiang, for the very tricky talk. Any questions?
Yeah, please.
Can you remind me like the modular part, like how do
Yeah.
you use it in modular? Yeah.
So here I only introduced the linear way of using this. It's like after you learn this F star, you can not only predict Y, you can predict any transformation of Y. If we restrict all the inference tasks as a prediction or estimation task,
Okay.
because this gives you the MMSE solution for all different targets.
The target should be a function of Y rather than some other.
Yeah, that's like the framework. It's like if you put a random Z and let me to predict, then I cannot do that. But in machine learning, it's highly possible your downstream task Z is highly related to Y. So that's why practically adaptation also works well.
Have you tried using that backwards pass to do something like generative AI?
Yeah, that's what I'm also thinking about.
Yeah, should be very soon.
Cool. Like how does it relate to like say diffusion type of models? I think diffusion model can also.
Diffusion model can be understood as something if you formulate as score function, then score function is also representation. Then it can be related in an interesting way. It's still some ongoing work.
See.
But I'm interested in talking about more. I mean, because this representation gives a way to extract useful parts, but how you use that is actually on top of how you get that. So I believe it's highly relevant.
Oh, let's thank the speaker again.
It's definitely a
Yeah.
It's not like there's something I think maybe I'm actually gonna try to ask what in the class.